section 3.8, derivatives of inverse functions and logarithms. We're going to first talk about some basics about inverse functions and the algebra of inverse functions. Now, just in general, I got here, inverse functions undo each other. Marriage and divorce are inverses, adding, subtracting inverses. Mathematically, not all functions have inverses. Only one-to-one functions have inverses. So, definition. A function f of x is one-to-one if a not equal to b implies that f of a is not equal to f of b. So this is saying that something is one-to-one if different input values, a and b, input values, different domain values, different input values always result in different output values, different answers. That if I put different x values in, out come different y values. That is the concept of one-to-one. This is saying a function is, I'll just repeat it right here. This is saying a function is one-to-one if different input values, domain values, result in different answers, range values. So let's just consider f of x equals x squared. And so if we find f of 3, without much fuss, we get 9. And if we find f of negative 3, we also get 9. So the point here is that x equal 3 and negative 3 both gave an answer of 9. So f of x equals x squared is not one-to-one. Being lazy there, instead of writing out the words one-to-one, write it that way. Okay, so we're going to be talking about inverse functions. It's a fact, or we'll get to a fact down here, that only one-to-one functions have an inverse. So we need to know how to determine whether something is one-to-one or not. And we're just going to do this algebraic or graphically. Algebraically, it can be a little bit difficult, and we don't really need to go into that detail. We're only going to do it graphically. And so we got the horizontal line test. A function f of x is one-to-one if there's no horizontal line that intersects the graph at more than one point. And then fact, a function f of x has an inverse if and only if f of x is one-to-one. So the question here, which of the following graphs represent a function that has an inverse? And so this is the same as asking which are 1, 2, 1. So when I look at this guy, which is just the parabola that we already looked at, but specifically, if I just draw a little line here, notice right there and there, approximately, guessing, definitely guessing, well, I should have been more careful with my line. If I had to guess those, well, I'm not going to bother guessing with them. Horizontal line intersects twice. So not one-to-one. So no inverse. And if I had to guess here, it looks like here that maybe this was like negative 1.1 and that gave me 1.9. And here maybe this was 1.1 and gave me 1.9, just guessing. But my different x values were giving me the same y value, so not one-to-one. And this guy is one-to-one. Over here, any horizontal line intersects at most once. So it is one-to-one and has an inverse. This happens to be the graph of e to the x, and I did that on purpose. We'll see that in a minute. So no inverse on this one because it's not one-to-one. Inverse on that one because it is one-to-one. So talking more about inverses, let f and g be inverses such that f of g of x equals x for every x in the domain of g, and g of f of x equals x for every x in the domain of f. Then f and g are said to be inverses of each other. So there's the mathematical way of saying that they undo each other. So what I said at the very top, inverse functions undo each other. The way a mathematician says things undo each other is with the composition statements here. So what this guy is saying is start with a number x, apply g, get that answer, apply f, and it goes back to your original number x. And then the same thing down here. It's saying start with a number x, apply whatever f says, get that answer, apply g, and we get back to x. Now, this is the mathematical way of saying that those two functions undo each other. And when two functions undo each other, you have inverses. Now, notation here, the inverse of f of x is denoted by f inverse of x. That is read f inverse of x. It is not an exponent of -1. It is our symbol for inverse function. And so then if f and f inverse are inverses of each other, when I do their compositions, they have to undo each other because that's what inverses do. Note, f inverse of x written that way is not 1 over f of x. The symbol f inverse of x always means the inverse function of f. To denote 1 over x with an exponent, you would write it that way. And that is a big deal. I will have students not learn that this symbol means the inverse function, and then they treat it as an exponent, and then the whole problem's just wrong. That always means inverse function. If I want to denote 1 over f of x, I write it that way with the whole f of x in parentheses and then a -1. Okay, properties of inverse. The graphs of inverses lie across the line y equals x. If the point AB is on the graph of f of x, then the point BA is on the graph of f inverse. Again, because they turn things around. If f of a equals b, then f inverse of b equals a. Again, they turn things around. They undo each other. The domain of f of x is the range of f inverse. The range of f of x is the domain of f inverse. So we will just keep those things in mind as we now start talking about logarithms. Okay, logarithms, and that did not come in that does not show up very well, so let's highlight that in some color. Why don't we highlight this in green? And so in green, we have y equals e to the x. Shown below are the graphs y equal e to the x and y equal natural log of x. Note the graphs reflect across the line y equals x. That if I dash that line, y equals x in there, and if I envision folding my paper along that line, y equals x, the two halves would lie on top of each other. That's my reflection property. The reflection property implies that y equal f of x and y equal natural log of x are inverses of each other. And in fact, y equal natural log of x and y equal e to the x and y equal natural log of x are inverses of each other. And you're just going to accept that as a fact because it is a fact. But then we can take stuff that we know about the exponential function and now find stuff about the logarithm function. So, we already know about the exponential function that the domain is -infinity to infinity, that, exponential function, your x is up in the exponent. You can have any number be an exponent. No one has ever told you you can have all exponents except 0. You can have all exponents except negative numbers. You can have any exponent you want. You can even have weird exponents like pi. Exponents can be any, in our world, any real number. We're in the real number world. And even if we open it up to complex numbers, you can use complex numbers too. But we're in the real number world. So can be your domain, your exponent, can be any real number, and what you always get out are positive numbers. Any number 12 raised to any exponent is always going to be positive. E raised to any exponent will always be positive. So the domain of the exponential function, negative infinity to infinity, the range, 0 to infinity. Well, then I can just take that information and kind of do a little crisscross here, because the domain of one function will become the range of the other, and the range of e to the x will become the domain of the natural log of x. So the domain of the natural log of x is 0 to infinity. So that's saying you can only take logarithms with strictly positive values, and the domain, or the range, is negative infinity to infinity. Because the domain of the natural log of x is 0 to infinity, it's important to note that the natural log of 0 is undefined, as are logs of negative values. This is true for all logarithms. Now you want to make sure that your calculator is set, and we're going to hit mode here. Not only should your calculator be set for radians, it should be set for real numbers. Make sure your calculator is not in using imaginary numbers, complex numbers. You pretty much want this first column highlighted. So note here, if I ask it to find the natural log of 0, it's not going to do it. Error domain. Natural log of 0 is undefined. And if I ask it to find the natural log of negative 3, again, non-real answer. We are not in this class going to do natural logs and negatives, and natural log of 0 is always undefined. It's true for all types of logarithms, because we are going to talk about other logarithms. Recall the number e. Recall e is the number in the definition, not recall, definition. Definition, e is the number in the domain of the natural log function, such that the natural log of e is 1. And you really should memorize that. I expect you to know that the natural log of e is 1. And recall, e is a number, it's about 2.718. And then we can see from the graph above of my natural log graph, we can see that as x goes to infinity, the natural log of x goes to infinity, or natural log of x goes to infinity. So as we go to the right, as x goes to infinity, my log curve is going to keep increasing. Now, it very slowly increases, but it keeps increasing forever. So as we go to infinity, natural log of x goes to infinity. And the natural log, the limit as x goes to 0 from the right is negative infinity. That if we go to 0 from the right, seeing what the graph is doing, it's going nearly straight down. And we'll conclude this video.